Hello everyone and welcome back. In this video we're going to explore polarization of electromagnetic waves. We're going to look at applications of polarization, the law of Malus, and solving polarization problems. Let's start out with some applications of polarization. Sunglasses are an obvious one. You want polarized sunglasses because not only are they going to be better at blocking the light, which is the whole purpose of sunglasses, but they're going to take care of the glare. Glare on a sunny day can be very blinding and it can kind of wash out the colors, and polarized sunglasses will prevent that. LCD screens as well take use of polarization. Polarization is basically a way to reduce the intensity of light. And if you think about a TV screen or your phone screen is very good at reducing the intensity of light. So for example, if you're watching a movie and there's a very bright scene, then all of a sudden, it becomes very dark, what happened? Basically those pixels let less light through. Less light was allowed to get through the pixel. And the way that happens is through polarization. I want to pull up for you a quick simulation that we're actually going to look at later, but this simulation is going to show us how polarization works. So notice that we have a light wave coming in, and in blue here is representing the electric field of that electromagnetic wave. The electric field is coming in, and it's going through this polarizing filter. And notice that this polarizing filter right now is not doing anything. It's not reducing the intensity of the light at all. But what you're going to see is that as we rotate this filter, notice what happens to the intensity of the light. The intensity is given by the amplitude of the electric field here. As you rotate this filter, the amplitude of the wave is getting shorter and shorter and shorter. And if you rotate it all the way to 90 degrees, you're going to cancel out that wave entirely. Okay? So when your TV screen goes dark because the train went into a tunnel and all of a sudden everything got very dark, the pixels are able to produce that darkness by rotating their polarization filter to block out all the light, just like you see right here. So for each pixel, there's actually a little polarizing filter that rotates to either make it very bright or very dim. Which is pretty cool. So let's take a look at our notes here, and our notes are going to really start with looking at what unpolarized light is. Okay, so we draw unpolarized light like this. Pretend that we're looking at light coming from the sun. Okay, the sun has a bunch of electrons that are oscillating and producing electromagnetic waves, and we have maybe one electron that's oscillating up and down like this, producing an electric field that's increasing and decreasing along this axis. But, there's going to be another electron that's maybe oscillating this way, right? Back and forth like this. Maybe another electron is oscillating this way. And you can see that really, in every direction, we expect to see electromagnetic waves and electric fields being generated. This is what we call unpolarized oops, that's a Z, unpolarized light. And we represent unpolarized light with this kind of scattered random direction for the electric field. Okay? What we're going to do is we're going to start by taking this unpolarized light and we're going to polarize it. What does that mean? We're going to run it through a filter that only allows the electric field in one direction to pass through. So check this out. Imagine that we had a sheet like this. So try to draw a sheet in 3D, like I have attempted to do there, and we're going to draw just a single gap in this sheet for the wave to pass through. Okay? So the wave is coming in, and it has this unpolarized light with these electric fields in all these different directions, but the only waves that can pass through are the electric fields that are in this vertical line. This axis here of this opening in the sheet is called the transmission axis. And the filter itself, this filter is called the polarizer. Okay? And what the polarizer does is it lets only electric fields through that are in the same direction as the transmission axis. So on the other side of this polarizer, we're going to have the light pass through, but only light in the direction of this polarizer. Now, you notice that if you think of these as vectors, all of these vectors have a component that's in the same direction as the polarizer, except for maybe these ones that are perpendicular to the polarizer. So each of these will let through some light. So that means that on the other side, we're only going to have electric field vectors that are in the same direction as the transmission axis. So following the polarizer, we call this beam here the polarized beam. And notice that the polarized beam, these electric field lines, are in the same direction as the transmission axis. Okay? Now, what's super awesome about this pattern is that it always yields the same effect. Okay? To talk about the effect, we first have to introduce a word called intensity. The intensity of light takes the letter capital I. The unit is watts. Remember, watts is a unit for power per meter squared. Okay? It's another way to say the brightness of the light. So a light that has more intensity is brighter, a light that has less intensity is weaker. And it makes sense that it's a function of 1 over distance squared, because as you go further and further from a candle, let's say, you'd expect the intensity to decrease. If you were right up next to a candle, if you have a candle right in front of your face, it's very bright. But as you get further and further away, as that distance increases, as 1 over the distance squared, you expect the intensity to get weaker and weaker, right? So the intensity, measured in watts per meter squared, is the brightness of the light. And let's call I1, or rather, let's call I0 the initial intensity of the unpolarized light. Okay, so I0 or I0 is the initial intensity of unpolarized light. Okay, let's call I1 the intensity after the first polarizer. So this polarizer here, we're going to call this the first polarizer, because we're actually going to add another polarizer later. But I1 is the intensity after the first polarizer. So if the unpolarized light has intensity I0, we're going to pass this light through the polarizer, and then the polarized beam is going to have intensity I1. Oops, you can't see that, can you? It's going to have intensity I1. Oh, you still can't see it. Now you can see it. There we go. Okay, so I1 is going to be the intensity of the polarized beam. I0 is going to be the intensity of the unpolarized light. Okay, now this relationship is going to work every single time. Okay, the unpolarized light, when you pass it through the polarizer, the first polarizer, you're always going to see the following. I1 is equal to 1/2 of I0. Please star this and smiley face it. This is a big deal. Okay, so for every problem involving polarized light, the first polarizer will eliminate exactly 1/2 of the intensity of the light. Okay, and we could prove this using vectors by saying that we're going to lose all of the horizontal components of the vectors, and we're only going to maintain the vertical components of the vectors to get through this polarizer. But we don't have to do that right now. We can just accept that the intensity is going to be exactly halved as a result of passing the unpolarized light through the first polarizer. All right, this is fantastic. And I want to tell you that this is going to be true regardless of the angle of the transmission axis. So even if this polarizer had been rotated a little bit, still only 1/2 the intensity is going to get through. Okay? It's just arbitrary that we chose the vertical axis to be the direction of the transmission axis. It could have been this way, And then the polarized beam would be this way, meaning horizontal, but it doesn't matter. All that matters is the intensity after the first polarizer is always 1/2 of the initial intensity. All right, very cool. Let's take this a step further. What if we were to take this light, this polarized beam here, and pass it through a second polarizer? This is where the magic happens. This is where things get very interesting. Okay, so let's take a look at what happens. Here we go. To further reduce the intensity, so if you want to make the light darker, for example, if you want to take a pixel which is bright and maybe shut it off, right? You went into that tunnel in the movie and everything has to get very dark. If you want to reduce the intensity even further, you add a second polarizer. Okay, so let's draw it out. Let's sketch the whole thing out. We're going to start with the unpolarized light, which is represented by these random arrows like this. This is the unpolarized light. Okay, and that could be from the sun, it could be from a lamp, doesn't matter. That's the unpolarized light. We're going to pass it through the first polarizer, which has this little gap through. Here's the transmission axis. Alright, and this is again the first polarizer. And you can therefore say that this is the first transmission axis. Okay? So, following the first polarizer, we're going to have our polarized beam, which is going to be I1. The unpolarized light, again, was I0. Okay? And now, we're going to go ahead and we're going to add another polarizer. Now, if we added another polarizer in the same direction as the first polarizer, that would be just silly, right? Because then all of the light's going to get through. But what if we rotated it? What if we rotated the second polarizer relative to the first polarizer? Let me show you what that would do. We're going to draw another polarizer like this. Okay? And notice that the transmission axis, represented with this dotted line, is at some angle theta from the first polarizer. Okay? So I'm going to label this angle here theta. And theta is going to turn out to be extremely important. Okay? So what we have here is an I1 intensity, which is incident upon a second polarizer. So this here is going to be our second polarizer. And this axis that you see here is going to be the second transmission axis. Alright, the second transmission axis. So, what do we expect to happen now that we are running this intensity I1 through the second polarizer? Well, the only light that's going to be able to get through is the light that's in the direction of the second transmission axis. So taking this electric field vector, passing it through this polarizer will only allow this transmitted light through. So again, we started with unpolarized light. We reduced the intensity by half when we went through the first polarizer. Now we're studying it through the second polarizer, and now the only electric field that can get through is the one that's in the direction of this second polarizer, and that's going to be very small. We're going to call this I2. And notice that these electric field vectors are very small compared to I1. So the question is, how much intensity gets through? And the answer to that question brings us to a very important law, which is called, drum roll please, the law of Malus. Okay, and the law of Malus states that the intensity following the second polarizer, I2, is equal to the original intensity that followed the first polarizer, I1, multiplied by the cosine squared of the angle theta. Okay, this can be written also as I1 cosine theta quantity squared, of course. All right. So, once again, I1 is equal to the intensity after the first polarizer. I2 is equal to the intensity after the second polarizer. And theta, and this is critical, okay? It's very common for students to make mistakes with theta. Theta is the most important and most tricky quantity in this entire equation. Theta is the angle between the first and second transmission axes. What that means is we don't really care what angle the first transmission axis was. We don't care what angle the second transmission axis was. The only thing that we care about is the angle between those transmission axes. Okay? And what's really funny about this function, the cosine function, is think about what angles can go into that function. So let's take a look. If theta equals 0 degrees, we all know that cosine of 0 degrees is equal to 1. 1 times I1 will just be I1. So you'll get back the exact same intensity that you had originally. And that's actually consistent with our simulation. And notice, at 0 degrees, you see all the intensity able to get through. So if this transmission axis is in the same direction as the second transmission axis, whatever intensity coming in, you're also going to get out from the filter. Okay? But as soon as we start to rotate that filter, you see the intensity getting smaller. Look how small that intensity got. And if I got all the way to 90 degrees, perpendicular to the transmission axis from the first filter, you see that we eliminate that entire wave. Nothing now can get through at an angle of 90 degrees. Okay? So let's take a look at our notes again. And we can say that if theta equals 90 degrees, cosine of 90 degrees, we all know, is equal to 0. So then no light's going to get through. All right. Okay. And one other way to represent that would be, imagine if you had an intensity I1 in this vertical direction, and then you try to pass it through a filter that was in the horizontal direction, right, perpendicular to that transmission axis. How much of that light can get through? We're going to say none. Absolutely none of that light is going to be able to be in the same direction as this opening, because all of these electric field vectors are in the vertical direction and this is in the horizontal direction, and therefore none of these vectors will be able to get through that filter. So on the far side over here, if theta equals 90 degrees, we're going to say that I2 is equal to 0. All right, wow, this is really intense. Good luck. If you have questions, please post them, and I'll see you at the next video.